All right, go.
Okay. An 89 kilogram man stands on a spring scale in an elevator. Starting from rest, the elevator ascends, attaining its maximum speed of 1.4 meters per second in 0.67 seconds. It travels with this constant speed for the next 5.8 seconds. Undergoes a uniform negative acceleration for 1.87 seconds and comes to rest. What does the spring scale register during the negative acceleration?
What?
Okay, so this is a 4-part problem, and
What?
3 or 4-part problem.
How long is this gonna take?
No, we're just doing one of the 4 parts.
Oh, okay.
We're just going to be focusing on the negative acceleration part. So really, we don't need all the information here. Some of the things that we do need to know, though. The mass of the man is 89 kilograms. We need to know that from the time where he's at his constant speed, where he is undergoing negative acceleration, where he comes to a rest, that means that his initial velocity in this interval would be the 1.4 meters per second. His final velocity is 0 meters per second because he comes to a rest. That occurs over a time of 1.87 seconds. It's not telling us what the acceleration is, but we do know there is going to be some acceleration. We are trying to figure out what the reading from the scale is going to be. Now, this would have been really easy if we were just having someone with a mass of 89 kilograms stand on a spring scale or a normal force measuring device.
Wait, show the camera.
Value.
Show the camera. There we go. All right.
Okay. But really, when we're asking what does the spring scale register, this is a way of asking for what is the normal force. What is that interaction between the spring scale and the person? So, if we're drawing that force diagram for this person, the first force that we should draw every single time ever is the force of gravity, pointing to the center of mass of the Earth. And then we're going to have that interaction between the spring scale and the person pushing up on them perpendicular to the surface we're in contact with. Because we have a negative acceleration, that means the net force will be down. That means our normal force has to be less than our force of gravity. So our sum of our forces here is going to be the force normal minus the force gravity. And then, because we're trying to solve for the normal force, we're going to go through this pretty much every single time we have a summation equation. We replace sigma f, the net force, with what it's equal to. If the forces are balanced, we can just write down 0. Otherwise, we're going to have to use Newton's second law of motion. Mass times acceleration is equal to sum of the forces. That's equal to our normal force minus our Fg, or mass, times the gravitational field strength of the Earth. To get the normal force by itself, we add mg to both sides. So it's mass times acceleration plus mass times the gravitational field strength is equal to our normal force. I can factor out the mass. So its mass is equal to acceleration plus the gravitational field strength, and that will equal our normal force. We are told the mass. We are told, but we should also know off the top of our head, the gravitational field strength, or the acceleration of gravity, but we still need to solve for our acceleration. That's where we're going to need to use the kinematic variables provided for us. The only one that would be really appropriate, I had erased it, so I'll just put it over here, is going to be our general equation from the ramp lab. Our velocity is equal to our starting velocity plus our acceleration times time. We know it ends up at rest. We know that they started off with the maximum velocity here, or maximum speed of 1.4 meters per second. We're solving for acceleration, we know the time. So to get the acceleration by itself, subtract the initial velocity from both sides, divide both sides by t. So our acceleration is equal to final velocity minus initial velocity over time. You guys might remember this as acceleration is equal to the change in velocity over the change in time. That was how we had it when we had a uniform acceleration, but really this only applies if that's an average acceleration, which it will be uniform acceleration while it's slowing down. But anyways, now that we have this, or rather this, we can just substitute that back in to this equation. Our mass times our velocity minus initial velocity over time plus the gravitational field strength is equal to our normal force. In this case, you just plug in the numbers that you have.
Is that the whole thing?
That's the whole thing.
All right, outro.
The thing again.
So this was not a problem that needed you to use centripetal acceleration, but this is an example of circular motion.
Oh yeah. Oh yeah.
The credits are rolling.
Yeah. I don't know how long.
That's it.